Okay, so there are a couple of data analysis techniques that I want to show you. Those techniques are cut-up point 3D and a point evaluation. Okay, so let's take a look at this problem. In this problem, we're asked to model a cantilever. So we're asked to construct a 3D beam with a width of 0.5 meters by 3 meters by zero point 0.1 meters, and we're told to fix one end of it and then apply a load on the top surface of 1,000 newtons. And we're asked here to find the total displacement of the beam at the free end, so that would be this end over here, and then give your answer in meters. And we're told we can take the material as nylon from COMSOL. So I've already built this model. Let me go ahead and pull it up. Okay, so you'll see that I've constructed a 3D beam here with a width of 0.5 by 3 by 0.1. Okay, and I've applied material properties here as nylon. So I've applied nylon from the built-in library. And then in the solid mechanics, you see on this end, one end, I've applied a fixed constraint. And then on the top, I've applied a load of 1,000 newtons. Now in my case, it's a positive 1,000 newtons because in the z-axis, my z arrow here, the vertices and the z is pointing down, so I know that's positive, and so it's pushing down on this surface. Okay. So previously I showed you guys how to get the results. Let me show you a couple more techniques here. So here's the default plot that would show you the results after the model is done. And notice that there are two things being plotted here. One is this one here, which plots the von Mises stress with the displacement. Actually, the von Mises stress doesn't show here. It's actually, the default plot is showing the total displacement. Okay, so and it's overlaid with the deformation on top. Okay, so actually if you click on this, anywhere you click on here, it'll show you the x, y, z coordinates of where you clicked, and then it'll give you the total displacement value here. Okay, so anywhere you click on this surface, so I'll go ahead and click on the very end here. You notice when I click on the very end here, it gives me the x, y, z coordinates, and it gives me this 0.03882. So that would be the total displacement on the end here. And you notice if you come here to the options, that is one of the options there. But that's not a very good way to get in a precise location. So let's take a look at a better way to do this. Okay. So a better way to do this is to either cut a point 3D or do a point evaluation. And I'll show you how to do both. Okay. Let's first take a look at cut a point 3D. So I'm going to right click on data sets. Okay. And I'm going to click on cut a point 3D. So this is going to allow me to define a point within the 3D geometry. So I click on it. Okay, our results are going to come from solution 1, and the coordinates I'm going to have somewhere on the end here, on the tip here. So let's just pick x0. So I'm looking at the x-axis here, and if I'm on the corner, that'll be x0, and in the y-axis, looking at the y-axis here, I know that this cantilever is 3 meters long, so I'll put 3 meters there. And in the z-axis, I'll just put 0 again. That'll give us the top corner. Okay, so I'll just put in 0 here. And then if I click plot, notice it gives me that point. Okay, so this is the point that we just selected. Now, if I wanted to get in the middle of the cantilever, I would just have to change the x coordinate. So I'll just try doing x 0.2 and plot that. And notice that it put me somewhere closer to the middle here. Actually, I think that this is 0.5, so it would be 0.25 would be the middle, right? Let's take a look. Yes. Okay. So now I can get data from this point by doing a point evaluation. So this point is called cut a point 3D1. Now if I go here to derived values and right click on derived values and then select point evaluation, okay, I can have the point evaluation, I can have the data come from the cut point 3D, okay, and so it's going to get the coordinates from this cut point 3D1, and it's going to display the displacement, which we're asked for the displacement, and all I have to do is press evaluate, and it gives the answer down here. Okay, so that's giving the total displacement from this 3D cut point that we put in the middle of the graph. Another way we could do it is here in the point evaluation. Instead of the data set coming from the cut point, we could have it come from solution 1, and then here select a point. Like for example, say I want to select this corner here. I just select that corner. Once I select it, it turns blue and it shows up here as 3. And now the expression is going to be this displacement. Again, we're looking for the total displacement. And if I press evaluate, it'll give me the answer here. Okay, so there's a couple of ways to evaluate the total displacement of this beam using two techniques. One, cut a point 3D if you want to select the exact point where you want to get the data from, or two, doing the point evaluation and selecting one of the corners and pressing the evaluate.